So now what we're going to talk about is eccentric loading. And this basically comes about, it's a way of placing an axial load on a bar and ending up with both axial stresses and bending stresses. Because up until now, everything we've done has been based on centric loading, which is right along the centroid. So let's take a look at a case of something like this. So we've got a bar with a little bit of jog in it. The centroid of the bar is at some distance d from the line of action where we're applying the force. So let's take a look at a couple of free body diagrams. So if I plunk it right there, and so what I have is externally, I have my load P prime that is pulling along that. Now, P prime and P are just the same, so we'll just say we have a load P. So what happens at that point? Well, internally, I'm going to have an internal load of P also. In fact, let's just, instead of making that a different color, we'll just highlight it to note that that is an internal load, not an external load. What's the force? What's the stress right there? Well, we know we do the sum of our stresses in the x direction. P is equal to P. It's in tension. We find the stress divided by the area. Fine. What happens if we look right here, though? So if I look at that free body diagram now, I have something that's shaped a little bit more like this. I have some load P that is being still applied on the outside edge. Well, now I have a couple of different things going on. Well, I still have some internal force. We'll call it F. Now, we'll just still call it P because we know if I do the sum of the forces in the y direction, that internal force is going to have to be equal to P. But if I leave it like this, what's going to happen is I'm going to have it rotating because there's an imbalance. So I'm going to have some moment internally that has to resist this. And so if I do the sum of the moments about this end point here, and we'll call this point is point C. So if I take some of the moments about point C, that has to equal 0 to keep it in static equilibrium. Well, what do I have? Well, I have that moment and it's acting in the positive direction. And then I look at this P value. This P is acting in a negative direction, so minus P. And I have an offset of D here, so that gives me my offset. So P times D would give me the moment. So then I have a moment force, and that moment force is going to be equal to that load times the distance that it's offset. So at point C now I have two separate loading conditions going on. I have an axial stress of P that I get from my sum of my forces in the y direction. And so that P is going to give us a normal axial stress. I also have a bending moment, and that's going to give me a bending stress. So I have two different stress conditions going on at the same point. How do I handle this? What's going on? This is where we're going to use the method of superposition. So if I take a look at this, what I have here is here's my axial stress. Here's my bending stress. So I solve each of those individually, and I superimpose them on each other. I add them together. And so this will give us the total stress. And as you can see, this is a combination of the two of them. I've just straight out added them together. So stress total is equal to stress axial or stress normal plus stress bending. And then how do I get that? I still put it together as stress total, and I just plug in what is my axial stress. Well, that's load over area. What is my bending stress? Now, we've used MC over I. That's our maximum. That's our biggest one. But remember, for at any point in there, we're looking at negative my over I. Once again, following the same rules as y. As we move towards the bend, it's positive. As we move away from the bending, it's negative. And why do we do that? Because if we have this case here, this is going to be compressive on the top. This is top part's going to be compressive. Bottom part's going to be in tension. So we move positive y, it's a negative number, it'll give us negative, it'll be tension, and then this way will be negative y, negative times a negative will give us positive, which will give us tension. Sorry, the negative will give us compressive, negative times a negative will give us positive, which will give us compression. So this is the basic formula for that, and we're just taking the two of them and adding them together. Now, we still measure y from the centroidal axis when we're calculating out bending. But you'll note in this particular problem, there's no neutral axis. We still have a centroidal axis, but not a neutral axis. So this is when we don't have pure bending, that's where things get messed up a little bit, because we always say, well, the centroidal axis is going to be the neutral axis. We're still calculating the bending on its own without worrying about the axial stuff. We calculate the axial on its own without worrying about the bending stuff, and then we just add the two of them together. There can still be a zero strain plane axis with a neutral axis, but most likely the eccentric loading is going to cause the neutral axis to be shifted off of the part and not actually be there. So it won't be the centroidal axis. So if you notice, so our bending here, we do have a neutral axis right here, the point where there is no geometric change. But you notice when we put them together, there is no neutral axis now because we have something going on completely in the entire thing. But once again, we do the axial on its own, we do the bending on its own, we add the two of them together, and then we have the eccentric loading.